Hello, hello. Right, we have got the last little bit of applications and forces to go. And after we've done that, there'll be only one section left of mechanics to go, which is to do with differentiation, integration, and stuff like that. And this is going to be to do with things on inclined slopes, something that we've looked at before, things involving friction, something we've looked before, and things which are attached to pulleys, something which we've looked at in previous units as well as a little bit last year as well. Okay, and what we're going to be doing is looking to put all of these things together, okay, so that we get like a complete problem with all aspects of things that we've looked at together, okay? And the way that this is going to work, we're just going to go through one guided example, one exam style question, and then it'll be up to you to try out the rest of the exercise yourself. But because we've gone through so many of these different aspects now, so because we've gone through all the different components, we're just going to see how do we put them all together. And you'll see that there's not much different to what we've done in previous videos and previous lessons. And then make sure that we can do it all ourselves. Okay? And the situation that we're going to be working with is the one that is currently up on screen here. So we have two particles. Okay, they're drawn as boxes, but they're particles. So all of their mass acts at a single point. They're 5 kilograms and 10 kilograms. They're connected by light inextensible string. So that's something that we could comment on in terms of our modeling. Okay, it's a light inextensible string, which means that the tension in that string is going to be the same at all parts of the string. The string passes over a small smooth pulley, so there's no friction in the pulley, and that is at the top of the inclined plane, okay? Like in the diagram which we've got here. The P particle rests on the inclined plane, and Q hangs over the edge of the plane with the string taut. Okay, so the string is already tight. Okay, the string is not going to go any further than where it already has. Oh, hit down frames and we're back. Okay, so just in case we missed anything there, the string is tight. It's not going to be getting any longer, and Q is hanging off of the edge of the inclined surface. The plane is inclined to the horizontal at an angle alpha, where tan alpha is 0.75. This is something that we've seen before. We should be familiar with how we can deal with this, as shown in the diagram. Boom. The coefficient of friction between P and the plane is 0.2, and the system is released from rest. So you can imagine that we're holding on to everything, and then suddenly we let go. Okay, we're at that instant where everything kind of just gets let go. We want to find the acceleration of the system, and then afterwards the tension in the string. Okay, now one thing that we're going to need to consider, as well as do we have all of the forces in our diagram, do we know where they all are, one of the things we're going to have to consider is how is this going to move? Okay, now if we had something heavy hanging over the edge of a cliff and something light attached to it that is on the cliff, we would imagine the heavy thing would pull the light thing down. Okay, so what we're going to hopefully, what we're going to assume from this is that Q, when we let go, is going to head towards the floor, and P is going to rise up the slope to meet the pulley. Okay? That's what we're going to assume. So we need to think about the forces that are involved. Okay? The weight of each particle is going to head vertically down. We're going to have friction opposing the direction of motion. So if the boxes are going to accelerate this way, going from P to Q, friction is going to oppose that motion. We should have tension in the string on both sides, and because the string is light and inextensible, the tension is the same in all parts of the string. And we've also got a reaction force of the surface against P, which is linked into the frictional force as well. Because this is only going to head straight down, there's not going to be any components of the weight for this. But because this is heading at an angle, there will be components of this. Okay? And the tan alpha part of things, that just means that if we had a triangle, that's where the whole of the paper is. 0.75 is 3/4. And that means that the hypotenuse of that triangle would be 5. So tan alpha is 3/4. Sine alpha is 3/5. And cos alpha is 4/5. Okay. That is what that tan alpha is telling us. It's telling us that we don't actually need to know what the angle is. We just need to know what the values of sine of our angle or cos of our angle are, just in case we need to find any components. So, our diagram. Here's everything that we've got. Okay. We've got the mass of this pulling it down, the acceleration is coming down, tension is opposing that motion, heading towards the pulley. For this particle, we've got our reaction, our friction, the tension, which again heads towards the pulley, and also the mass, which we've resolved in components. The mass of the particle here is 5, so this should really say 5g cos alpha and 5g sine alpha. So we want to find the acceleration of the system, and to do so we basically want to try and write as many equations as we can for the different parts of the system that we've got. Okay. So let's first think about Q. So at Q, we know that the overall system is going to be accelerating downwards. Okay, so 10g, take away the tension, that's the overall forces being resolved, is going to equal the mass, which is 10, times the acceleration. Now the acceleration of the whole system is going to be the same. Okay, that's one of the assumptions that we're going to make. And we can make those assumptions because of what we've said in the question, the tension in the string being the same, the light inextensible string, and the whole system is just going to release with the same acceleration to begin with. So that's one equation. I've got too many unknowns. I can't solve that just by itself, so I'm going to need to have another equation. So we need to look at, not R, it's called P. Read the question. So this system, we're heading off this way. So tension is overriding the forces pulling back down the slope. So T, take away 0.2R, and also take away mg sine alpha. Okay. And that is equal to mass times acceleration. Now, in this case, the mass is just 5, so let's actually write that in. Right, so let's take a look at what we've got. Now, I've got some things here which I can work out. I have that sine alpha, and I have that in the from our little angle triangle thing at the top. I don't know what r is yet. I'm going to have to also find out what r is equal to. Now, to find out what r is, I'm going to have to look at the components that go perpendicular to the plane. Okay, so we're going to resolve going perpendicular to the plane. Here we resolved going parallel to the plane, and here we resolved vertically. So perpendicular to the plane, we have r is equal to mg cos alpha, or 5g cos alpha. Now, 5g, that's just going to be 5 times 9.8. Cos alpha is 4/5. So I've got 5 times g times 4/5. Oh, just gone off there. There we go. We can fit everything. The 5s will cancel out. So we've got r is equal to 4g. So substituting, we have that t take away 0.2 times 4g, take away 5g times sine alpha, which is 3/5, equals 5a. Now, all of this stuff we can look to simplify. Okay, we could type that into our calculator and just get a number. But let's just do some practice. So the 5s will cancel out, leaving us with 3g. 0.2 is the same as 1/5. So that's going to be the same as 4/5 g. So -3 take off another 4/5 is 3 and 4/5 g. So t take away 3 and 4/5 g is equal to 5a. Okay. Now, realistically, if you're in an exam scenario, you're going to want to just type this into your calculator and just get an answer for it. But you can look to do these things without a calculator if you're wanting to. Now, where do we go from here? We had an equation for involving t and a at the top. We have a second equation involving t and a at the bottom. We've got two simultaneous equations to solve. Where this is equation 1, this is equation 2, or the other way around. Your calculator is very good if you've got one of the Casio ClassWiz ones at solving simultaneous equations. They will do it for you if you program it incorrectly, and then we can go from there. Alternatively, we can rearrange this, substitute in for t, and then use that to find a value of a. And that's what we get. Okay. -3 and 4/5 g is the same as -3.8 g, and everything else I think matches up. Now, for the tension in the string, we can just take one of our two equations. We found out what the acceleration is. We can just substitute back in to find out a value of the tension. Okay, and there we go. Job's done. Jobs are good. And hopefully you can acknowledge that at this point, although there's a lot of stuff going on in here, and towards the bottom a little bit more stuff than we actually need to go into, but the individual processes here are not that involved compared to some of the integration problems that we were looking at in Pure, or even, some of the problems that we were looking at before, okay, just resolving, finding components, introducing friction, angles, but also the tension in the string for the pulleys, okay? And that is revising some of the stuff that we did in year 1 as well, to do with tension. So we want to see now if we can recreate something similar for ourselves. Okay, so we're coming from May 2013. We're looking at question 3 of an old M1 paper. We have a similar kind of scenario as to last time. And we want to find the tension in the string immediately after the particles is released. Now, before, we had to find stuff out before we could find the tension. This time we're trying to find the tension immediately after the particles are released without any previous stuff. We're going to need that diagram. Now, exams are generally pretty nice in giving you some kind of diagram. I'm not. So I'm going to say that the first thing that you need to do is to construct your diagram, taking in all the information that is on there. Okay, so we're going to see in 2 minutes, can we construct our diagram with everything fully labeled? So, our diagram. This is the picture that we're imagining. Okay. And we need to make sure that everything is labeled. Okay. So, what have we got? We've got the components of the weight that act parallel and perpendicular to the 2 kilogram mass. We've got the friction, which opposes the motion of the 2 kilogram mass. We've got the reaction force of the 2 kilogram mass and the tension in the string that acts towards the pulley. For the 4 kilogram mass, we've got the weight of that, which just acts vertically, and we've got the tension, which again acts towards the pulley. So, our next objective, this was 9 marks. We've spent 2 minutes of it drawing a diagram, which means that we've got 7 minutes left to see if we can solve the problem and find the tension in the string immediately after the particles are released. Okay, let's see how we do. You may want to first of all look at what the forces are when resolved for each individual particle, just as we did before. So hopefully we're nearing the kind of the finish, or have finished with this problem. Looking to find the tension immediately after the particles are released. Right, so let's take a look at the mark scheme with this and see how all the marks get kind of distributed. Okay, so we've got first thing, which is to establish an equation of motion for B. Okay, the weight take away the tension is equal to mass times acceleration. Not too bad. 2 marks apparently. Equation of motion for A, the tension, take away our frictional force, take away 2g sine 30 is equal to mass times acceleration. Okay, and a decent chunks of marks there as well. Notice that they give us a slightly different thing here, which is a use for a different method. Resolve perpendicular to the plane to find a reaction force is 1 mark by itself. And then use of the friction equals mu times r. Now our coefficient of friction is 1 over root 3, which if you know your trig values is, I believe, tan 30. So times 2g cos 30. Okay, you can use these things to do some cancelling out, which equals just g. So using that frictional force back in our equation of motion for A, we have T, subtract G from our frictional force, subtract 2G sine 30. Sine 30 is a half, so that just comes out being take away G. So T take away 2G is equal to 2A. It's at that point that we then look to solve our equations simultaneously. Okay, and to find out our value of T. Okay. Yeah, we just doubled this equation to make it equal 4A, make the two equations equal to one another, but these processes here are essentially for solving your simultaneous equations. Okay, to get T is 8g over 3, or 26.1 newtons. Now that DM1, I believe, stands for a dependent method mark. Okay, so dependent on other things that you may have done previously in the question. Okay, and that's it. There we go. That's putting everything together that we've got for friction, components, resolving forces, pulleys, all those kinds of things, put all together in one kind of question. Okay, and it's all of those things put together that make some of the mechanics problems that little bit more daunting to start off with, but when you get used to the method of what you need to do and what you need to look for, they become relatively manageable. Okay, especially when you compare it to some of the other kind of problems that you might do in other papers for A-level maths. Okay, and this is where I stop and you kind of look to take over. Okay, the exercises in the Excel books are paged there. Should be able to get access to them online, and or use your own textbook source if you have something different. There's only one further unit to go from this, and because Easter is approaching, I might find some other way of getting that to you, either by just giving you lesson slides or by continuing these after Easter. I don't know yet. I haven't thought that far ahead. Okay. Incidentally, as well, Ofqual released some guidance to do with grading for the summer. If you can find it, I'm assuming it will be plastered over news sites very soon. You may want to have a read of that if it interests you. Have a wonderful day. Looks like it's going to be a really nice day where I am. Hopefully it is near you as well. and hope you can make a nice day of it. Thanks for tuning in if you have. I will see you some other time.